So I will go through some methodology, move on to result, and then some future work. The site is in Windsor, which is at border of Ontario and Michigan, Detroit. So this is a river separating the two cities, and this is the bridge connecting those two cities. Detroit and Windsor are so-called automobile capital of the world. Less so today compared to 7 years ago or 50 years ago. Still, there are a large amount of manufacturer activity going on, including the so-called Tier 1, Tier 2 supplier and assembling. There are also other industrial activities like power generation, refinery, not directly in this region, but in the surrounding regions. For example, the power generation in Ohio is significant, and other Midwest states, upwind of Windsor, they're quite heavy on industry. For Windsor itself, there are significant transportation sources because the bridge connecting Windsor and Canada is significant to the trade between those two countries. Every day, tens of thousands of vehicles crossing the bridge. The mobile emission might be an issue. So the objective is to look at the temporal variability, including diurnal, day-of-week, seasonal, and interannual, and also the relationship between TGM and other pollutants, and with TGM and meteorological conditions, also to what extent we can explain the variance in the hourly concentrations. So that's my primary interest. And then statistically, the so-called outliers, if we remove them, do we have a more clear relationship? Those are the primary interests. The monitoring site is fairly close to the bridge on University of Windsor campus. We only did TGM. The sad story was I got funding about the speciation unit for a number of reasons. I could never get university agree upon a site which has enough juice to power the system and also secure enough for frequent change of the denuders and so on and so forth. In the middle of that, we're building new buildings, moving, and eventually I gave up. So my Tycoon 2537 operated for 4 or 5 years beautifully and then break down. My speciation unit, brand new, still sitting there. Maybe next workshop I'll auction it out. The weather data was in Windsor Airport, which was roughly 10 kilometers in this direction. Okay, that's the only weather station we have in Windsor. And other pollutants, Environmental Canada operate 2 air quality stations. One of them is 2 kilometers, another is 1.5 kilometers. We just choose one in downtown because CO was monitored in that station, not in the other station. The 5-year study period, in the later 2 years, we encountered some instrumentation problems. Here is the result. The annual TGM, we excluded year 2010 and 2011 because of missing data in certain seasons. If you look at later slides, the seasonality is quite significant. So when data were missing from some seasons, it's probably not fair to do the annual anymore. Overall, there's declining trend during those 3 years. However, we do realize 3 years is too short to do any decent trend analysis. Based on the limited data, the trend is consistent with a decreasing trend observed by other Canadian mercury stations and also in the wet district network in United States and Canada, also some background station measurement in the middle of nowhere. Overall, the concentration level during the 3-year period is 1.8, which is second, if not third highest in Canada. If you recall the chart Daniel showed based on Amanda Cole's study, there was one station in Canada which is right next door to a large point source. So the reading is over the roof all the time. After that, Windsor is either the highest or second highest. This is again because of the unique location. It's an urban site with substantial industrial influence in the nearby region and also by long-term transport. Monthly, there are high concentration during the warmer months, with the exception of July. I'll talk about this later. And then also during the cold months. We believe this is because of increased power demand in the heating in the summer, in winter, and also the cooling in the summer season. That region of the United States, Canada, we have a distinct fall season. Summer is hot. Most people turn their AC on, and winter is cold. The low number in July could be potentially due to the industrial shutdown. Most facilities in that region have a 2-week, if not 3-week shutdown during July. Employee will take time off, enjoy vacation time, and then the facility will go through some instrument maintenance, facility upgrade, so on and so forth. That could be the potential reason. Now move on to seasonal. The seasonal trend is high in summer and low, relatively high in winter, and low in those two transition seasons. This trend is very different from what Huiting has been reporting for years, which is, I believe, spring high and fall low. Right? Again, we believe this is because of a unique location of Windsor, being an urban site, have a heavy influence from industrial facilities, and those reflect the mercury increased anthropogenic emission during the summer and winter seasons. You can also see from this, and every chart I've shown, the distribution is not normal. Any way you look at it, it's not normal. The center line, hard time finding there. I have to press harder. The center line is medium, and then the dot is mean. The mean is always about medium, sometimes significantly. So this is fairly close to log normal distribution. It's not normal at all. Day of week, very clear trend. You have lower concentration on Saturdays, Sundays compared to weekdays. The difference in either mean or median is roughly 10%. We believe this indicate in the study region at least 10% of the weekday observation is due to industrial activities in the region. And then diurnal. This is a unique too. The concentration increasing until daybreak, still increasing, still cranking up. We believe this is because of the building up during the nighttime. When day breaks, there are strong mixing. However, the industrial activity, power generation also kick up. And during warm season, the re-emission is there too. For that reason, you're not seeing a dip as seen in lots of other studies, including Alberta. You're seeing continued increase, and then all of a sudden, right afternoon, you're like, boom, there is a huge decrease, very steep. We believe this is because of photochemistry with oxidant, and also the strong mixing, because the mixing height in the afternoon in the region like Windsor and Detroit is fairly high, a couple of kilometers normally, unless there is a significant amount of cloud. And then in the evening hours, it continue to increase. This trend is different from most trend observed in Canadian sites, because most Canadian sites are in so-called rural or something similar. We look at the diurnal trend by season. Similar trend in spring, split trend in summer, fall, and winter. It's just the summer is much higher. Okay, and you also have a steep decrease here because of photochemistry. The depletion in spring started earlier. Our hypothesis is, again, you have photochemistry. In Windsor, when we look at the seasonal ozone concentration in spring and summer, the spring concentration is only a few ppb lower compared to summer. However, in summer, you'd have re-emission because of the vegetation. In spring, there's not much because Windsor don't have a full season per se in terms of spring. It's so short. We do not see lots of green until early May. Okay, for that reason, we believe you see, in fact, photochemistry kicking in very early on, but there's not enough re-emission to compensate that. Okay, now, that's then plus PCA plus 1 rows, that was the paper submitted to Rob's spatial issue. The rest was cut off because I feel either Rob or reviewer will kill it instantly. Now, so far, we have a very nice story. All the diurnal, so on and so forth, the temporal variability, we would be able to explain, use the knowledge we have about photochemistry, emission from man-made sources, re-emission from soil and vegetation, so on and so forth. However, if you want to put a number there, and then the picture is not that pretty anymore. So qualitatively, we could explain lots of what's going on, but quantitatively, let's look at what happened. So I run a NOAA one by one, means each time I only look at one factor. They're all significant. Again, I didn't use 2010, 2011 because of some missing data. So you look at season only. So R squared is 2.6 something, and if you look at year, it gets smaller and then become decimals. Okay? When all of those are included in the ANOVA, it gets something like 5.4%. So all those factors, all those pretty box plots combined can only explain 5% variance in the data set. Okay? I was a little bit disappointed. So I say, oh, there are other pollutants, there are miserable conditions, because at any given time, there are lots of things into play. You have chemistry, you have weather condition, you have re-emission, which you cannot measure directly, but somehow could be reflected by solar radiation. And then if you put a 2 hours lag, so that's your soil temperature, right? So I did some statistical analysis. Turned out those variables are more significant in compared to others to explain what's going on. So I put them one at a time. Okay, so it's forward stepwise regression. NOx first, only 2%. I use adjusted R squared because the more variables swim in, the lower the significance. Everything is significant, just low number. Plus temperature 3%, plus ozone 3.4, plus temperature 3.7, and the list goes on and on. They're all significant. And then the more variable you add, it gets higher, but it just, the incremental increase in your R squared, it becomes not significant practically. So that's what happened. All beautiful pictures, but when you look at numbers, it's simply not there. So there are a lot of things we could not explain using the temporal factors and the observations of other variables. Okay, so we look at the correlation between TGM and other parameters. I apologize for the fairly small font. Maybe you cannot read. Because of the significant seasonal trend, we look at all data combined and also by each season. Okay, you can see the number are all awfully small. The largest we have is close to 3%. Those are R, not R squares. If I square them, it's like 5% or less. Okay, so no single variable can explain 5% or more of the variance. Okay, and however, the directions are indicative, and most of them are statistically significant, although practically almost meaningless. The positive correlation with the co-pollutants, indicate combustion as a common source, and then the negative correlation with ozone indicate photochemistry, and then the correlation with wind speed and pressure indicate transport. Okay, overall, there is a lack of strong correlation because I believe there's too much scattering. Okay. Of the request of the reviewers, we also did a non-parametric test. The results were similar. Okay, now I zoom into TGM and NOx because one-on-one NOx is the number one co-pollutant, could explain what's going on. A little bit more than a few percent, I guess. On the far left, the top left chart, this is again the TGM seasonal trend. And then this is a NOx seasonal trend. Okay, you can see on this part, until this point, not too bad. However, there is a dip in the NOx you didn't quite see. in mercury yet. Mercury will decline later. Okay, so this is a scatter plot all by full season. Now you can see this part. Okay, when NOx is low, you somehow have a high concentration or have a large variability. The concentration could be low, could be medium, could high. So this is the region that interests me. Okay, it's not entirely out of phase in this part, but something else. How many minutes I have?
You got 5 minutes. Four minutes.
Okay, thank you. I thought you were signaling me.
No.
Okay, now I concentrate to in the full season because it's easier to look at one another other than full. Okay, we start from the again TGM and NOx. So this rectangular identify the region there might be some problem. The TGM still fairly high, and then the NOx reached the minimum already. Okay, on the one-on-one, so I did a hourly average. So 24, 24, and then this is the correlation. So this is the area. So we have seen large variability. Move on. So I thought maybe I could reproduce it by doing something, which I tried. Okay. We start from here. Gosh, where's my? We start from here. This is the scatter plot of hourly data, and I did hourly, seasonal hourly, hour-of-day average. Now you can see this somehow represents. This is not your typical linear regression. The common variance assumption is seriously violated. Anyway, it's kind of resemble. So from here to here. And then from here, I get, for each point, I get mean and standard deviation because I knew it was a log normal distribution. So I recreated this using the mean value, hourly mean value, and standard deviation, make it close to log normal. And then now you compare this one and this one, there's something not quite right here. There's a strip of data missing because, again, log normal goes both ways. And if you have 20 subtract 25, it will become negative. Concentration cannot be negative, so it's removed. So I'll fix it later. Okay. So what I'm trying to do is to try to say, when we know there are a lot of factors into play, but if we can do something to identify a different season, different time of the day, maybe one factor is more predominant than others. So that's the storyline I'm chasing. I'd be happy to hear from everybody if this is a crazy idea or there's some hope to get something done. Okay, and then lastly, we look at the effect of outliers. Again, I did a general linear model. All factors included in the model are significant, including all those we have talked about, and those. When everything combined, say R squared is 21%. Not impressive. If I remove hourly TGM greater, gosh, I have a hard time with it. Hourly TGM greater than 12, this is the mean plus 6 times standard deviation. So anything beyond that will be removed. And then also then R squared increase. So there are a lot of things going on leading to low variance being explained. One of them is the so-called outliers. So if we want to figure out on a day-to-day regular basis what is influencing the variation of TGM, maybe we have to remove the outliers or do something like identify the top 10 percentile and remove them and say what happened. I'm still hopeful. There must be a story there. Very quickly, summary. Gradual increase during those 3 years, season, high in summer and winter, low in spring and fall. This reflect the site being in urban setting and have fairly strong industrial influence. The day of week is higher on weekdays as expected. And the diurnal pattern similar in spring, in winter and fall. In summer, there is steep decrease. And in spring, the depletion start fairly early. Again, those are similar to some urban sites in the region. And in terms of temporal variability, the factors through the statistical analysis in order of importance are season, year, hour of day, and day of week. However, there's a lack of strong correlation with other parameters, including other pollutants and meteorological parameters. The high TJM or large variability of TJM event seems to be associated with when other air pollutants are low. So I'm going to code those hours and then further identify which hour it happened, which season it happened. What else? Overall, there's a clear trend with a lot of parameters. You look at seasonally. However, you look at hour by hour, it being washed away. And the overall low percentage variance explained by the temporal factor and environmental factors could be due to a number of factors, such as large variability of the data itself, or the outliers, or something we have not identified yet. Almost done. Okay. So I will spend more work, unless everybody here tell me, oh, don't chase it, Iris, it's a crazy idea. SO2 is another thing I want to look at because it's highly right-skewed. Finally, huge thanks to my undergraduate students who helped me a great deal during the course of the project. Herschel, Mark, and Elizabeth. And the equipment is funded by NSERC and also HackerRun, who gave me a friend and family discount. The Operation Fund provides NSERC travel assistance, University of Windsor. I sincerely thank the editors of the special issue and the anonymous reviewers for their constructive comments and suggestions. This one will be published soon. Thank you all.
Is there any questions?
Yes.
Yes.
I have a comment, I should say. I would assume that if all the parameters keep constant, all conditions are constant, just one parameter changes, then that parameter should explain 100% of the variation, right?
Okay.
Okay. So the reason you only see 2 or 3% is because each parameter, if changing individually, can cause 100%, but all the rest of the parameters might cause 97%. So the net effect would be just 3%, 2% for every variable. So if you have a very, very large data set, one approach would be to split the data set into very small subgroups with other dominating parameters as constant or very close to constant. The other approach is that if you don't have a huge data set, you could use the average. Let's say just like the regression paper I presented yesterday. We couldn't see a good correlation between the partitioning coefficient and temperature. Like 8 out of the 10 sites, you get R squared less than 0.2. But if you split the data into 2-degree bin, you average all the data within the bin, which means you averaging out all the other variables, we get R squared as high as 9.5.
Good idea.
Yeah, that could be another approach you exploring that.
Thank you.
By the way, I used the first approach on the drug deposition data, and I did find a better correlation because I used the same friction velocity condition. I split all the data night and day, and subgrouped all the data into same friction velocity condition. I did find a better correlation between the deposition velocity with relative humidity and with other parameters. Okay.
Yeah, thank you again. We also thought about using HYSPLIT to separate, just similar to Daniel has done, separate them into different flow regimes, say what happened. Yeah, there are lots of things I want to play with. Thank you again.